All right, the Hangout is live, as Google tells me. So the way these office hours work, I try and solicit some questions in advance, which gives me a chance to prepare diagrams. And in computer vision, often you need something to look at to know what's going on. And this week we had a pretty good question from Jean Fertiers, who I haven't seen arrive yet, but I still think it's worth addressing, about how we go in the problem set from the output we get from Hoff lines to actually having shapes or higher visual concepts like objects, in this case street signs. And I've put together a presentation on that. I think it's actually going to take a good part of the 40 minutes I've set aside for questions, and then we'll have 20 minutes for general questions, anything you want to talk about at the end. I'll try and have pauses in the presentation to take questions from the audience, but if at some point there's something I say that seems really weird, stop, we'll pause, we'll talk about it. I make mistakes all the time, and you get 3 hours to prepare for this, so there's definitely a good chance you'll see something that isn't quite right. So with all that said, I'm going to pop up some slides I prepared, and we'll start from there. Okay. So I'm forcing this to always be presentation on top, so if you speak, your video won't pop up. If it seems like we're having a good discussion, I'll turn off that feature and we can all talk and sort of have video chat, which is the whole point of doing this on Google Hangouts. So I'm going to go through sort of 5 topics. I'll start with a brief talk about what's the big picture, what are we trying to do, and what we're going to talk about today. Then I've got a fairly large section on building intuition for the d theta representation of lines, which is different from the mx plus b. This is a big part of the 2b lectures on the Hoff transform, but I'm going to talk about it in the building up and identifying polygons from this representation. Then I'll present just a basic algorithm for finding polygons with a known orientation, which is really one of the main tasks in the homework. I thought long and hard about if I want to actually share my code for that or just share pseudocode. And eventually I decided pseudocode, because otherwise we get 200 homework submissions that all look the same, and our plagiarism detection software goes crazy, and Pedro comes and yells at me. So instead, we're going to just go through a pseudocode algorithm, and I'll also show you some results from the real code algorithm so you can trust me that this thing actually works. I'll talk a bit about how you could expand the algorithm to finding polygons with unknown orientation. And finally, I'll say a little bit about all the complicating Scott says, Jean just put in Piazza, getting a video call is full air. Options, yes. I think that we can link to the YouTube broadcast here. He won't be able to do video chat, but he will be able to text. Let me post a quick follow-up on Piazza there. I'm going to stop sharing my screen briefly and All right. Would someone who's in office hours now mind checking the YouTube link I just posted to Jean on Piazza? I'd like to double check. All right. Would someone who's in office hours now mind checking the YouTube link? Actually, I was able to just see myself talking. That's always a disconcerting experience. So it does look like the YouTube link is working, and I've just got to check if, yeah, and I think anyone can chat there. All right. So just to recap, we're going to go over Jean's question about how to actually go from the lines that the Hoff functions give you to actual representations of shapes, and then to objects. And I'm going to share my screen again. Okay. So let's just dive into it. There's a big picture that comes up a lot in computer vision, especially classical computer vision, where we try and build pipelines. And I've got a very basic graphic of what a PS2 pipeline might look like. But the idea is you start at something very primitive, like pixels, and then you can get something a little less primitive, like edges, for example, using the canny operator, the canny edge detection. And maybe you can get those edges to make lines using the Hoff transform. And then maybe you can take those lines to shapes and those shapes to objects. And if you watch through all the lectures of this class, you'll eventually hear Professor Bobek talking about going even farther and from objects to scenes and from scenes to activities. So in this problem set 2, we're trying to show you, at least give you a start on this sort of pipeline, a classical computer vision pipeline. And we're asking you to fill in the links that take from lines to shapes and from shapes to objects, object labels. And in this case, it's a very limited, stylized thing, but it's kind of good practice in getting into sort of the classical computer vision world. And there are some good reasons to actually want to think like this. We've got some evidence that the human brain works somewhat like this, and that we can actually find layers in the human brain that find things like edges and corners on MRIs. And if you deconstruct some of the neural networks people are building that do this whole process all in one go, those also seem to trigger the lower layers on low-level things like edges, lines, and corners. So what we're doing makes sense, and that's the big picture. And for this office hours, we're going to dive in pretty deeply into this connection between lines and shapes. And before we get too deep about lines and shapes, we're going to try and build some intuition for this d theta notation that Professor Bobek likes to use. And I actually think it's a very powerful way. It's by far my favorite way of thinking about lines and parameterizing lines. And so this is a review of lecture. I'll go pretty quick, but the basic idea is we can define a line not by the mx plus b, but rather by defining the distance from the origin. And this is the shortest approach distance. So it ends up being a perpendicular distance. This angle where my mouse is right here is a right angle. And theta, the angle of that line from the x-axis. And I'm not going to try and be too formal here. So I'll note that there are a lot of definitional problems you can get into, especially with theta. And you've got to know what your implementation of the line algorithms you're using work with. For example, does it return angles in degrees or radians? And for this office hours, we'll use degrees in 0 to 360. There's wrapping of angles, so angle repeats. You can have, if you have an angle greater than 360 degrees or less than 0, you can fold that back into the range. And this is something that actually is annoying and devilish all throughout the computer vision classes, working with angles and some of their properties. So this will be good practice for later. Another point I wanted to note is that we're actually in this problem set trying to find line segments. which are finite points on lines. And if you run the standard Hoflines algorithm, which is Hof lines, you end up getting back full lines, which are infinite. And sometimes that can cause some problems when you're getting this into an algorithm. So I promised you I would talk about shapes. And so the first, I wanted to go through a little exercise, a set of a few slides saying, if we look at the parameterization of the three lines that make up a triangle using this d theta notation, what do those look like? And I think this is going to, hopefully, if I do done my job at all well, suggest an algorithm pretty immediately. So if we look first at this green line, the first thing I'm going to do is make it dashy and long, because it's a real line that is going to, once we parameterize it with d and theta, that represents the entire line to plus and minus infinity. And it's got some distance here. I'm not going to be very formal about the distances because these axes don't have any units, and it would be an exercise in futility. It's not very important. What's interesting is the angle is 30 degrees. And what's very interesting is you can imagine moving this triangle around, and that angle is always going to be 30 degrees. Its d is going to change. And you might say, wait, what if you shift the triangle up? Doesn't that change theta? But it doesn't, because theta is always the shortest path line. It's not the shortest path distance. It's not the distance to a particular point. It's the distance to the shortest point on the line. So we'll always have theta as 30, even if we move this triangle around. So we can do something similar. Now we're looking at the bottom line, which is blue. You can imagine a little dashed line that's d here coming down. And this line has theta as 90 degrees, because this angle right here is 90 degrees. And finally, we can put in another line here for the red. And already we start to get in some ambiguities with angle. I look at this and I think, of course, that's negative 30 degrees. But in the scheme I mentioned earlier, it's actually 330, because you have to go all the way around. And you just have to be careful with how your angles are defined and what you're getting out of Hof lines. But what's interesting is now we have sort of a concept of a triangle based on lines, and in particular based on the angles of lines. So a 30-degree line, a 90-degree line, and a negative 30-degree line define a triangle. And what's nice is they define a triangle, for the most part, independent of translation and independent of scale. And hopefully you're thinking, aha, in the p-set we have things that change position and they change scale. They don't change orientation. So this is maybe a property we can exploit, that the thetas for these lines always fall in a nice pattern of sort of 30, negative 30, and 90. So I want to, at this point, take a brief pause and ask, does anyone have any questions up to this point on what we're doing with the d theta orientation of lines and how we've sort of built up a concept of a triangle as being three lines at 30, 90, and negative 30, a triangle in this orientation? All right, seeing no questions, onward. So our next slide says warning in big bold letters, which means it's important. Hopefully you've all woken up from whatever you're doing during office hours. The warning is that if we translate this triangle down here, our red angle goes from negative 30 to 150, because this line now passes on the other side of the origin. This is, again, a place where you've really got to understand how the particular implementation of Hof lines you're using implements angles, and if it implements a sign distance. So some Hoff lines will give you an angle 0 to 180 degrees, likely in radians, and then a positive or negative d depending on which side of the y-axis this point falls on. Other Hoff lines implementations are going to give you an angle of 0 to 360 degrees, probably again in radians, and give you an always positive d. So when we get into the algorithm discussion, I'm assuming a Hoff line implementation that I haven't thought too deeply about. So I want to put a fair warning that you've got to understand these little details before you go too much farther when you're implementing this. And as a final point, if we had 3 lines that made up a triangle, we'd like to be able to find out the vertices of that triangle. And that's not actually too difficult because we can find line intersections by solving a little system of equations. And we've got an equation that defines a line. This is pulled straight out of lecture. D is equal to x cosine theta plus y sine theta. And Professor Bobek is bad about if this is a plus or a negative sign, so I've chosen a plus, but hopefully it will be pretty obvious how this changes if you're using a sign convention that has a negative there. And at all the points at the intersection, or at any point where 2 lines meet, you've got to satisfy the equation for line 1, which I'll denote with a subscript 1, and the equation for line 2. So you can set up this little system of equations and you can solve it however you like. You can sit down with a piece of paper for 10 minutes and write out what x and y are analytically, or you can trust in NumPy linear algebra.solve. And we have a question, does D play a role if we want to differentiate between multiple triangles? It can. I'll talk about differentiating between multiple triangles later on when I get to complicating factors. D probably isn't the best way to distinguish, but it can help. All right, so with this, we have all of the pieces to sort of build an algorithm for finding a polygon with a known orientation. And I've thrown together some pseudocode, and because I don't want to give you the answers, this is very pseudocode. I don't deal with edge cases. I abstract away some nuance and expect to spend more time on this than copying it into PyCharm and defining some variables. So the way this little function works is I say, I'm going to find a triangle, and I'm going to give it the lines and the orientation. And orientation is defined relative to sort of the triangle I was showing on prior slides, so one where the point is up. And so I've said there are sort of 3 valid angles, 30, 90, and 330 degrees. And we're going to adjust all of those by the orientation. If the triangle is twisted, then all those angles just change by the orientation as 1. And so I have some big array of lines from my Hoff transform, and I just say, if a line is in the valid angles, like if it's a good one, then it's one of the sides of my triangle. Once I have all of the sides of my triangle, I can find the 3 vertices by just finding the intersection between those lines. This pseudocode loop does 0, 1, and 2 inclusive, which means you get 3 vertices, and we return them. And right now, you're all hopefully very annoyed with me because this code ignores some things that are important. And in particular, the Hoff transform is susceptible somewhat to noise. It has a resolution. So we can't just say, is an angle in this array of angles? We have to worry about noise. And that's actually a pretty simple fix. It's you use some tolerance band when you determine n. The bigger problem is, what do we do if we find too many lines? And you almost always will. If you have a scene that's anything other than just a triangle on a white field, there are going to be lines beyond just the 3. And there are 2 ways to approach this. The easy way, and I think the more correct way. And the easy way is to simply take the best 3. So the OpenCV implementation of the Hoff transform returns lines in ranked order of strength. So how many votes they got in the Hoff accumulator. So we could take the first line that gives us 30, which is also the strongest line with an angle of 30, the strongest line with an angle of 90, and the strongest line with an angle of 330. And that's what I did in the implementation I whipped up to show you some results. I think what's actually a slightly better way to do it, but I haven't done it, is start with the best, but also do some consistency checks on your triangle. And an example of some consistency checks you can do is you can check, are all the vortices on the page or on the plane of the image, are the vertices you find, if it's not a triangle but a square, is it really a square that it's a regular polygon, or is it actually a rectangle? And you can add a lot of checking to this part to reject certain triangles, which would make this algorithm more and more robust. But for right now, I'm going to show some results just taking the best. And I felt that I couldn't throw up a pseudocode algorithm without at least showing some results from a real implementation. I'm not going to share that real implementation because then a big part of the homework is done. But here's it applied to the basic yield sign image, which is a triangle. And it immediately picks out the 3 vertices. I know you haven't been asked to define vertices. You've been asked to find the center. But that's a pretty simple operation. The center of a polygon is just the average location of its 3 vertices, or 4 vertices, or n vertices, where n is the number of sides of the polygon. So this is pretty encouraging. I was pleased to see this result because it meant I had something useful to say to you today. I was even more pleased to see this result. And I want to note that when I showed at the very beginning of office hours this pipeline, that's for a reason. And the reason I showed it is the parameters from those early canny functions and the Hoff line matter when you start to get noise. And it's always good to look at images from each stage of your pipeline. I had to do a bit of parameter tuning, especially in canny, to sort of get these to fall in the right spot. I'll also take a moment to note that you might be wondering, why did it find the outer triangle and not the inner triangle? That's a nice side effect of we chose the 3 strongest lines, so the strongest 30-degree line, the strongest 90-degree line, and the strongest whatever degrees this was line. And so these outer edges are just a little bit stronger than these inner edges, and it happily finds the right triangle, the one we actually wanted. They're stronger because there are more pixels. It's a bigger triangle. And finally, I wanted to say, if I take this very simple algorithm that sort of is 3 angles separated by 60 degrees and apply it to a real yield sign, does it work? And it turns out it does, again, with a little bit of parameter tuning to get a good edge image out of canny. So hopefully this at least justifies to you a bit that this can work, this relatively simple representation. I'd like to talk for a few minutes about why it works, and is this something I just invented, or is it actually tied to the course material? And surprise, it is tied to the course material. This is in some ways a poor man's generalized Hoff transform. So in the generalized Hoff transform, you have a bunch of edges in different orientations that all point towards the centroid, or vote for different centroid locations. Here, instead of having pixels on edges vote for a centroid, we're in some sense having edges vote. And the specific orientation of different edges is very, very similar to the way things are defined in the generalized Hoff transform. And in fact, if you wanted to spend many hours coding, I think the generalized Hoff transform would be an even more robust way to solve this problem set, but it's probably not necessary. You can sort of do this poor approximation where you just look for lines with consistent angles. All right. This isn't something you need to know for the problem set, but I feel like I'd be a somewhat poor TA if I didn't try and at least teach something interesting. And you can ask, that's great, but what if the triangle's rotated an unknown number of degrees? And there are two ways to solve this. They're both hinted at lecture, although I think method 2 comes a little later on when we start talking about corners and Harris corners and things like that. But method 1 is we take our known orientation solver, bin orientation, say into 360 degrees, and just run it again and again. And somehow we choose the best one. That's not trivial. And it can be computationally if you need an accurate estimate. The other method is to realize that what really makes a triangle is sort of this delta of 60 degrees. So rather than negative 30, 30, 90, it's that you have sides that are offset at different angles. And you can sort of imagine writing a fine triangles function that says, we look at our first line, and then we see if we can find a second line such that the difference is 60. And if we do, we find a third line such that the difference is 60, and then we're done. There should be a break in the loop there. And then you can find the vertices in the same way, and you can return them. This also suffers from high computational complexity. Just from an inspection, sort of, we're actually looping over 3 variables. There's a hidden loop in each of these finds. So this has potentially an O of n cubed worst case behavior. You'll find in computer vision, at least my experience has been, that a lot of the classical computer vision is very, very computationally intensive and involves lots and lots of iterating over possibilities. You also see that in the lectures with Professor Bobek. The entire Hoff transform is an exercise in iterating over many variables. All right, the last thing I have to say is, gosh, it's really annoying that you have to find the orange box and the yellow box, because that messes up this method I've just described. And I'm not going to tell you how to solve it, in part because I haven't coded it up myself, so I'm not 100% confident. But when I look at this, I see 3 possible approaches. And one is to go way back in the pipeline and say, let's not let this be a problem. Let's ensure that by the time we get to our shape finder, we never have an image that has 2 squares in it. And you might be able to do that with a mask based on color. Essentially set everything that isn't in a narrow color region to black, and then feed that image through. So that's sort of a cheap way to avoid the problem. You'll also note that we've used almost no information about where the lines fall in an image in all of this. We've only cared about their orientation. And by ignoring where lines fall in an image, that sort of let us avoid questions about scale and translation. But it also means that we can't take advantage of spatial separation. And so you could start to wrap that image back in. And there's another implementation of Hoff lines, a probabilistic one in OpenCV, that instead of giving you d and theta, gives you the endpoints of line segments. So you could try and assign segments to objects by saying, oh, I see a cluster over here, and I see a cluster over here. Now I'm going to run my object finder just on the lines in this area, or just in the lines in this area. And finally, I wouldn't be a very good computer scientist if I didn't note, here you're going to have 8 lines, and here you're going to have 8 lines. It's not that big of a problem to just try all the combinations and see which one gives you 2 distinct squares versus some weird rectangles. So that's what I have as sort of an answer to the posted question. And I appreciate everyone listening to me talk for 35 minutes. At this point, I want to open the floor to questions, to discussion. It can be about what we just talked about, or if you've got some questions about other parts of the lecture, I'm always happy to talk off the cuff. I'm just going to briefly check Piazza, make sure people aren't lost there. I actually see 2 questions that have popped up on Piazza, so I'm going to tackle one of those at random. Brandon Moss says, just now, how does the Hoff algorithm decide when to cast a vote? In the case of a binary image that is run through a canny edge detection process, is it just that there are 2 or more white pixels on a single line? And then a vote is cast for the d and theta parameters that describe that line. In the gradient extended version, the algorithm casts a vote for the d and theta pixels that describe and have the same gradient. And Anthony says we're typing in the YouTube chat as well. I can't see the YouTube chat. Let me see if I can pull that up. I apologize. This is my first experience on YouTube Live, and so I'm okay. I can see some live chat, but I don't see the history of it. I see 2 questions from Vitaly. So I'll start with the question from Piazza, from Brandon. The Hoff transform, you typically feed into it an edge image, and every white pixel casts a vote. At least in the standard Hoff transform was presented in lecture. Black pixels present no votes, white pixels cast a vote. It's again sort of this pipeline concept we talked about right at the beginning, is you have to have a good input that is typically a binary image, and that forms the input to your Hoff accumulator. I have seen some extensions of the algorithm that you can say, based on how confident you are that an edge is an edge, instead of giving it a 0 or a 1 value, you can give it a probabilistic value, let's say 0.5 probability of being an edge, and then that gets voted into the Hoff accumulator. I don't think the default OpenCV implementation does that. I think it's just every non-zero pixel gets 1 vote for a line. So you have to have already passed your image through some kind of edge detecting filter to then feed it into the Hoff transform, which is finding lines. Hopefully that answers that question. I see Vitaly has, is there a name for an algorithm for detecting a triangle? Not that I'm aware of. This was just, I looked at the problem, I said, is there an easy way to solve this quickly that doesn't involve getting into a sort of deep vision algorithm and that I can present to get people started? So I don't know if it has a name. It's really, as I said during the lecture, sort of a poor man's version of the generalized Hoff transform. So the generalized Hoff transform says, the generalized Hoff transform, you sort of have, I'm trying to draw a shape that Professor Bobick has in lecture. His is much better, but puts together a bunch of lines, and then pixels vote based on gradient direction. So if I find a pixel on a line with a gradient direction, it votes for a centroid there. And it votes for a centroid there based on the different orientations of all of these lines. Oh man, questions are rolling in. This is great. This is great. Okay, I'm going to start with Yogesh's question. He says, in the context of the generalized Hopf transform, there was talk about training and recognition, but in the method you propose, where does the training part come in? So the method I'm proposing doesn't have a training part. We tell it what we're looking for. In this case, 3 lines that form a triangle with differences in angle. You can also, so there are many generalizations on the Hopf transform. You can feed in a bunch of examples and build up your template from that. You can also do template matching, where instead of just pixels on a line, different features of a car, say, vote for the centroid of the car. That's another example that was shown in lecture. And that's a little beyond what we would do on this problem set. But you can imagine training, we sort of look at a lot of cars and say, this little pattern occurs this distance from the center a lot of the time, and build up our data set that way. Hopefully that answers that question. Vitaly asked, do we have to use the H transform for detecting the different shapes in the image? No, you don't have to do anything in this problem set. The only restriction is that you aren't allowed to use the forbidden functions. If you think you've got a simpler, better, more interesting way to solve the problem, go ahead and do it. Do keep in mind that the auto-graded portion of this assignment is probably the easy part. The part where for your report, you apply your algorithm to the noisy image or the image with multiple signs, or to real street signs, are the times when your algorithm is really going to be stressed. Jean says, gosh, sort of just answering the questions rapid fire. Jean says the OpenCV implementation of Hopf-line circles has a parameter for the canny portion of it, so it seems like it does an edge detection part. Do you still suggest we pass it an edge image? Gosh, I've learned something I've forgotten. Let me look into that, and I will post an answer to it on the Piazza thread for this office hours. You do want to have full control of the canny parameters you're using so you can get a good edge image. The only way I was able to, in the presentation, find the noisy yield sign and find the yield sign in the real world was by tuning my canny parameters a little. So I don't know if the part of the Hopf pipeline in OpenCV lets you configure things to the degree you might want to. Brian Newbold says, I was able to find circles by passing a Gaussian blur to Hopf circles. I didn't use canny. Did I just get lucky? It sounds like, no, what Jean said earlier is John's a smart guy. I think he was an AI with me last semester, so it's likely true that the OpenCV implementation has a canny portion. I apologize for missing that. It's one of those things where you never actually get an error if you put a canny before the Hopf portion of your code. It just kind of looks like it's working because it's doing the canny twice. So that was my mistake. And finally, I'm catching up on these questions. Anthony says, can you talk more about the accumulator you are referring to in the CV2 Hopf transform? Would we need to know how to implement this algorithm? You should have a good idea of how the Hopf algorithm works. In particular, the accumulators and the transform, not necessarily for the problem set, but there will likely be some questions about Hopf accumulators on the final exam when we come to it. It used to be that in this class, we, for problem set 2, asked students to write their own Hopf algorithm. And that's a very interesting experience. It's very low level, working with pixels in the image. If I share my screen again, and go to this first slide where we're talking about pipeline, the Hopf transform lives at a very sort of low level, going from edges to lines. And we thought it would be more fun this semester to let you guys work sort of at the upper upper reaches of this pipeline. And also the Hoff algorithm tends not to be fun to implement. It's got a lot of edge cases. There's a lot of sort of off by one errors that can occur. So it ended up being more of an exercise in frustration than a learning exercise, which is why the problem set has changed a little. But we do expect you to understand the algorithm. It's certainly fair game for the final. We haven't written the questions yet, but I'd be shocked if there wasn't something that tests a fairly deep understanding of how Hoff goes from edges to lines via voting in an accumulator. All right, so I have answered, I think, most of the questions I see on YouTube chat and on the group chat here. Let me go to Piazza and see. Okay, I see a question from, I think, Willie Way. And in P-set2 assignment, why is radii range 1031, but the circle in sample t1.png has a radius bigger than 29? So I try not to answer logistical questions in office hours because it's always very frustrating to find that some important logistics were shared in minute 47 of an hour-long office hours video. So I'm going to make a note here to pass your question on to Pedro and see if I can get a good definitive answer rather than speculating on if there's an error in the assignment or if there's not. I don't think there's a good chance I would mislead you somehow. For question 2, can you shed some light on the questions from 190? What is the rationale between disallowing functions that find peaks, but allowing functions such as Hoff lines and Hoff circles? So I'm going to peel back the curtain a little on the problem set design process. One TA is generally leading the design of a problem set. And for problem set 2, that was Pedro, who shouldered a good chunk of the work. So I can't comment definitively on his goals, but I can speculate a little. Writing a correct Hoff algorithm in 2 weeks is hard. When I took this class, that was assignment 2, and I put in about 40 hours chasing down edge cases and errors. I think that other students did similarly. And at some point, you aren't learning how the algorithm works. You're learning that it's a very finicky algorithm that takes a lot to implement. So that's the reason we're allowing it this year and trying to push you guys to the higher end of the pipeline where there's more room for experimentation, more room for innovation. And I think you'll find as you get to the last bits of the report, also quite a bit of room to work very hard or be very clever. But we didn't want to force you into just the very low level pixel by pixel. Is this buffer 1 too short? Am I off by 1? Should I be counting from -pi to pi or 0 to 2 pi sort of questions that tend to arise when you're implementing the Hoff algorithm from scratch. I don't know the answer to why we're disallowing find peaks. There might be some clever ways to do peak finding that you get around the intent of the assignment, but that's entirely speculation on my part. I'll make a note to also point Pedro towards that question so he can give you a definitive answer. Yeah, let's see. So Vitaly asks, could I post my PowerPoint to Piazza or somewhere? And I think I will, yeah, I'll post it to Piazza along with the recording of this office hours. I'll probably post it as a PDF rather than a PowerPoint. It's actually, I use Linux, so it's an ODP, which is the LibreOffice format. So rather than subject all of you to the conversion errors, I'll just dump a PDF on there. Let's see. Yeah, so that's I think everything I have, and it looks like the various sources where I'm seeing questions are working. Are all empty. I'd like to turn this back on you guys and ask, is this a useful format for office hours for you? I'm thinking back to my undergrad, and office hours was often, the professor talked for quite a bit, but there was also some interaction between the students. Is there a way that I can do a better job making this an educational experience for you? Okay, great. It looks like I've been helpful. I'll be sure to ask every office hours. This is when I think I've done a good job, if I'm doing well, because always great to be praised. I'll add that computer vision tends to be very diagram heavy, and it's hard to talk about. I find that when I'm working on this stuff, I'm continuously drawing on a whiteboard or sketching on a piece of paper. So it makes life much easier for me if prior to office hours you answer the office hours questions. I think I'm going to try or post questions to the office hours thread. I think I'm going to try and put out my call for questions on Tuesdays rather than Wednesday morning. If you ask a good question there, there's a chance you get a 17-slide PowerPoint with diagrams and things, rather than me just talking off the cuff, that I think is a little more helpful for everyone. I think we've got time for one or two more questions if anyone has anything. Vitaly, will Project 3 and Project 4 also be so 40 hours demanding like this one, Project 2? Gosh, that's a subjective question, but two things are happening as you take CV. One, you're getting much better at NumPy and Python really quickly. It's probably the best introduction by fire to the topic. You learn a lot of quirks. So things get easier, and you learn OpenCV functions by heart. It becomes second nature to type CV2 canny. So it improves. The problem sets get more mathematical. Problem set 3 starts to involve some linear algebra transforms, and the how hard that's going to be for you is really going to come down to how much familiarity you have with math and solving systems of equations rather than coding like this assignment. Problem set 4 I can speak to a little bit more because I'm designing that one primarily with plenty of help from the other TAs. But problem set 4 is about detecting motion, and it can go quite quickly if you're familiar with the equations and have really internalized what Professor Bobek is saying about the Lucas-Canati transform. But if it doesn't click, it can take a very long time and be a P-set that people could struggle with. So I think my answer is they have the potential to be hard P-sets, but they can be easy if you take the time to internalize the lectures. I know this is a hard class, and we do try and keep it balanced. If there is a PSET that ends up taking everybody 60 hours, please tell us about it in the CIOS survey at the end of the course, or if you're willing to be not anonymous, just mention on Piazza that an assignment was crazy, because we want you to sleep. Okay. When I'm looking off the screen here, I'm not ignoring you. I'm just sort of skimming through the different sources of questions. I've got a dual monitor set up. I think with that, it's been a busy office hours with a lot of questions, but I think we're reaching a pretty good stopping point. I'm going to call it now 3 minutes early, and that'll give me time to hopefully tonight see if I can get a link to the broadcast posted and also get the slides as PDFs posted. Thank you everyone for attending. Really appreciate it. Come back next Wednesday for more fun. Bye now.